Welcome everyone to this week's edition of HoloTube. We are very happy to have Luca Delacretaz from the University of Chicago with us today. And you can see the title. The screen is yours. Luca, please take it away.
Okay, thanks, Matthias, and thanks a lot for giving me the opportunity to talk. It's nice to see some familiar Zoom names, especially people I haven't met in a while. This talk will be about the local equilibration time, okay, which is the timescale that interacting systems need to reach local thermal equilibrium. So, we know that every interacting system thermalizes, and the way it does this is that it first reaches local thermal equilibrium, and then what usually happens is that hydrodynamics emerges and controls the much slower global equilibration towards thermodynamic equilibrium. So this global equilibration time depends on system size, right? It's going to grow with system size, whereas the local equilibration time is really an intrinsic characteristic, an intrinsic property of the system that you're studying, and it's in a sense a kind of intrinsic measure of its interactions, because you need interactions to thermalize. So I think it's a very important quantity that I like, and so this talk will be mostly about this quantity, this time scale. So this time scale in weakly coupled systems, we have pretty good, let's say sharp definitions of what this equilibration time should be. You can think of it as the scattering time or the mean free time of quasi-particles. So the time scale your system needs to lose memory of its initial conditions, because its components have scattered enough times. Okay, so this requires a Boltzmann description. And in these contexts where you have a kind of weakly coupled Boltzmann description, this time scale is going to be parametrically large. Okay, it's going to go like 1 over a cross section, and those cross sections will be very small at weak coupling, where you have perturbative control. So, and this makes sense because weakly coupled systems will take a long time to thermalize, right? Particles don't see each other. So systems can take as slow as they want to thermalize, but what has captured a lot of people's attention in the past few decades is that it seems that quantum many-body systems can't thermalize as fast as they want. There seems to be a universal limit, a quantum limit, on how fast many-body systems can thermalize, and this has led to the conjecture of a Planckian bound on this equilibration time. Okay, and this conjecture kind of came from a combination of experiments and examples, in particular in holography of systems that are strongly coupled. So you might expect this quantity to go down and down as you increase coupling, but eventually that stops, and there's a kind of limit to how fast the system can thermalize. There's also been a lot of interest in this bound due to its possible relevance for strange metals, for this linear in temperature resistivity. Because if you think of, loosely speaking, of resistivities as scattering rates, then you could imagine this would kind of offer a paradigm for linear in temperature resistivity as all strange metals saturating a bound. So I'm going to distance myself a little bit from this specific linear in T resistivity motivation, but ask the somewhat broader question of whether there exists a universal, quantum statistical mechanics bound on equilibration times, okay, on all quantum many-body systems, where hopefully this timescale can be universally defined, okay, beyond just this Boltzmann type definition. And what I'd like to convince you of today is that the answer is yes. One can universally define this timescale, and it satisfies a bound. So this might actually, let me skip this slide. So this might remind you of another timescale that or a rate that is commonly studied in the context of strongly interacting systems, thermalization, and chaos, namely the Lyapunov exponents, which are a kind of measure of chaos in classical and semi-classical systems. So they're defined by this out-of-time ordered correlator, and in large N systems, you can extract an exponential growth at early times of these correlators. And this rate is kind of similar to the rates that I'm talking about, 1 over tau ek, in that they're both the rates are both very small at weak coupling, okay, perturbatively small, and at strong coupling they seem to be bounded. Okay, and in the case of the Lyapunov exponent, there is a sharp bound that one can prove. But I'd like to argue that this equilibration time tau is much more universal, much more well defined in general. So in particular, it doesn't require large n. Okay, this exists in any many body system, strongly interacting, weakly interacting, whether or not close to semi-classical limits. And it's also more experientially relevant because it appears in every correlation function. Okay, you don't need to look at these funny time-ordered correlators, which are probably difficult to engineer, experimentally. So it's very relevant. On the other hand, it's proven more difficult to constrain. Okay, we don't have such a nice sharp bound on tauic, and this is partly due to the lack of a consensus on a good universal and sharp definition of the equilibration time. So the first part of this talk will actually be devoted to the humble task of defining sharply, both sharply and universally, what I mean, or what one should mean by local equilibration time. Loosely speaking, the punchline will be that one should think of this timescale as the timescale where hydrodynamics or diffusion or whatever your hydrodynamic regime is emerges. Then in the second part, we'll see how we can place a bound on this timescale. From careful knowledge of hydrodynamic corrections and hydrodynamic fluctuations. Okay, hydrodynamics is an effect. You should think of hydrodynamics as an effective field theory. It's interacting in general, and so it has corrections. Every observable has a bunch of corrections at late times, and these corrections can become large. So, like any effective field theory, hydrodynamics knows about its own breakdown at early times, and this is what allows one to place a bound on how early hydrodynamics can emerge. Okay, it's basically the scale, the strong coupling scale of hydrodynamics. And finally, in the last part, I will show you some numerics where we were really able to kind of make precision tests of these effective field theories in both classical and quantum systems, both to kind of confirm, a lot of these more subtle effective field theory predictions, and also to use effective field theory to help difficult numerics, in particular quantum numerics. Okay, and those are based, so the numerics is based on work with my collaborators, in particular my student, Ruchira Mishra, and Alex Michailidis and Dimitri Abanin, who did a lot of this numerics. Before I start, let me pause here for questions, and let me also say that you should interrupt me at any point. I don't need to make it to the end. I think it's more interesting if there are a bunch of questions.
Can I ask something just as a clarification?
Yes.
1 over t, I mean, for ultra-relativistic systems, 1 over t is the distance between degrees of freedom, if you want to, I mean, they're not localized in quantum mechanics, but you can think of it this way. Does the bound also, for example, if you take mass to infinity and you have a chemical potential, so the number of degrees of freedom is constrained, does the bound still work as 1 over t, or does it work as 1 over the number of degrees of freedom?
Okay, there's several aspects to your question. There's the relativistic versus non-relativistic aspect, and there's the counting a number of degrees of freedom. So let me tell you but let me try to answer everything. So the hope or the expectation is that this is basically the bounds with no factors, essentially with no extra factors, in the sense that we don't have. Well, I'll define what this left-hand side is in a bit, but there aren't counterexamples. Okay, so the expectations as it works for any system. When I think of it as a bound on a time scale, there's no factor of speed of light or anything. So it's really we expect it to hold in non-relativistic systems with conserved number. We expect it to hold in spin chains. We expect it to hold it essentially anywhere. Where I'll be able to prove it, that's a slightly different, I'll be able to prove it in a much more constrained setting. In particular, I'll focus on CFTs, which, indeed will be relativistic. But the dream, I think this bound has the potential of being true in essentially any many-body quantum mechanics system.
Because just as a sort of in large and C, the way this bound is written is a little bit sort of subtle, because large and C has infinite heat capacity. So for any finite amount of energy, you have 0 temperature.
Yes.
And that's why I was asking about conserved degrees of freedom.
Yes. So large N will play an interesting role here. So it's kind of, yeah, we'll see how large N enters. But indeed, here I want this to be temperature and not energy density, and that would make a big difference. Although what I'll be able to prove is more like energy density, actually. So there will be, yeah, we'll see this in a bit. Maybe that we'll come back to your question at that point. Very good. So let's start with the definition. So, as I said, in weakly coupled systems, I think we have a pretty satisfactory definition. One could just compute scattering rates, okay, and a thermally averaged scattering rate would give you a sharp definition of the equilibration time. But I'd like to have a definition that applies both at weak coupling and at strong coupling in any system, okay, whatever the degrees of freedom are. So I'll start with something that you shouldn't do, that you can't do in general, but it's very tempting to do. So it's tempting to look for operators whose correlators decay exponentially in the thermal states. Okay, this is a thermal expectation value, real-time thermal expectation value. If you find such an operator, that seems like a very good notion, right, of an equilibration time. It's this decaying exponential is a very sharp way to extract a time scale. But the reason you can't do this is that, in general, is that exponential decay actually does not generically occur, precisely due to hydrodynamics. So let me illustrate this in a simple model, in a simple spin chain. We'll look at a QFT in a bit, but let's start with a spin chain, which has even fewer symmetries. Okay, so this is just 1D, 1 plus 1D system, spins on a lattice. These are Pauli matrices. It's just the Ising model with both a transverse and longitudinal field. And this model, it turns out, for generic values, of these couplings is non-iterable. So we expect it to thermalize, and it does. And the only conserved quantity is energy. So the only hydrodynamic degree of freedom is energy density. Okay, so there's diffusion of heat in this model. Diffusion emerges at any non-zero temperature. So what do correlation functions look like in this model? Well, the 2-point function of energy density certainly doesn't decay exponentially. Okay, it's a hydrodynamic quantity. That's pretty obvious. It will decay diffusively, and so this is what diffusion looks like in 1 plus 1D at the same, if you evaluate the 2-point function at the same sites, but late times, you'll get this 1 over square root T polynomial decay. Okay, diffusion is a kind of long-lived mode. Okay, so it's obvious that if we want exponential decay, we need to cook up some, consider a microscopic operator that's not the energy density. So here, just to be clear, HI is this whole thing, okay, the Hamiltonian density. So let's consider another operator. Let's say X at point I. So this operator X will, and let's look at its 2-point function. And the point is that this operator will essentially have the same 2-point function at late times because there's no symmetry that forbids it from overlapping with energy density. Okay, there's no quantum number that forbids this kind of diagram if I represent things this way. So its correlation function at late times will essentially be exactly the same as the energy density correlation function, up to some number that measures basically the overlap of that operator with the energy density. Okay, so it's also going to decay polynomially with the same power. So this seems like it's easy to fix. I can just by hand subtract the overlap of my operator with the energy density. Okay, and construct the operator xi minus some number, basically this overlap times the Hamiltonian density. That will be some slightly more complicated lattice operator. It's going to decay faster than this. Okay, by hand, I'm going to kill this term. But if you do this, the point is that so it decays faster by construction, but you still get polynomial decay because now there's no symmetry that forbids your operator to decay into 2 heat excitations, okay, which you can represent diagrammatically by this. Okay, and you can actually check this. So there's, really, this is happening. And at this point, I think the pattern is fairly clear. You could keep on going and forbid more and more terms, but there's an infinite possible decay channels and, without infinite fine tuning. So essentially any local operator decays polynomially in this model. Okay. There's no exponential decay. You can do this in field theory too. Here's a simple example of a field theory with no internal symmetry. Okay. So this is just regular, it has Lorentz invariance, translation invariance. So you'll have diffusive modes and sound modes, which will propagate along a sound front, and you have diffusion. So this is what the stress tensor 2-point function would look like. But the point is that if you choose any microscopic operator, phi or phi squared, it's essentially going to have, up to some, you'll have to sort out the indices and so on, but it's essentially going to have very similar 2-point functions as the stress tensor. It has various components of the stress tensor, so it's going to have polynomial decay in these regions. And again, you could remove these overlaps, but you'll never get rid of this hydrodynamic pollution of correlation functions. So good. So what can we do? So we don't have exponential decay, but I think the strategy is, instead of kind of suffering from this hydrodynamics pervading all these correlation functions, one should use our knowledge of hydrodynamics, and particularly the fact that we know what systems thermalize to, right? So thermalization is a complicated process. It's going to be very different from system to system, but every interacting many-body system thermalizes to hydrodynamics, right? And then depending on your symmetries, you'll have slightly different hydrodynamic modes, but they all thermalize to hydrodynamics, which then controls the slower global equilibration.
Luca,
So
could I ask a question here?
Yes,
Sorry to interrupt.
please. Yeah, no, go for it.
On this point, so you showed the hydrodynamic correlation functions and the decay rate polynomial. That's slower than exponential, but isn't that expected because those are protected by conservation laws? And shouldn't we, for thermalization, look at the degrees of freedom that are not protected, or quantities that are not protected? The thing is that
generically there are no such degrees of freedom, not because everything's conserved, right? There's only one conserved quantity, but everything is allowed to overlap with it in this particular QFT. So the phi squared, phi squared operator is not the stress tensor, okay? It's decaying polynomial. So yeah, okay. And if you have symmetry, if you have like a Z2 symmetry, then you could have found an operator maybe that doesn't overlap with hydro, right? If there wasn't this phi cube term. So sometimes there is exponential decay. I'm not saying there's never exponential decay. I'm just saying it's not generic. So it shouldn't be used as a, yeah. Yeah, thanks for the question.
Thanks.
Right, so it's not generic. So we want a definition that's going to apply to any system. And a definition, at least, a kind of loose definition for now, that will apply very generically, is to identify this equilibration time with the time scale at which hydrodynamics emerges. Okay, the kind of hydrodynamization time, as some people would call it. And this is essentially what a lot of people already do, in particular in numerics. So let's say you're doing numerics on some system that diffuses. You look at the density 2-point function. It has this 1 over this polynomial decay, okay, which involves the charge susceptibility, the diffusion constant. And in your numerics, you're not going to see this polynomial decay at arbitrarily early times. You'll see something else that will be not universal. And usually you would kind of try to identify, check that you indeed have diffusion at very late times, and then maybe fits to this form, and then say, okay, choose some error that you allow, and you could identify this thermalization time, this equilibration time, as the time scale at which you only have 10% error from hydro predictions. So there's some slight arbitrariness here, but at least qualitatively, this is a very practical definition that's already used by many people. But we can actually make it sharper by using our knowledge of hydrodynamics. So hydrodynamics not only tells us this leading diffusive decay of hydrodynamic correlators or other correlation functions, it also gives us a way to systematically organize all corrections to this behavior. Okay, it's really an effective field theory that tells us that it has an infinite tower of irrelevant corrections that will give small corrections at late times to power law corrections to the leading diffusive behavior. And there's qualitatively two sources of corrections in hydrodynamics to the leading behavior. The first is higher derivative corrections to hydrodynamics. Okay, for example, in the considered relation for diffusion, to take a simple example, you can have these higher derivative terms. Here, let's say I have rotation symmetry. I'm going to have 2 gradients, and grad squared in the case of diffusion translates into frequency omega, or 1 over t. Okay, so these higher derivative corrections all come with integer powers of 1 over t. In this case. And another source of correction is are fluctuation corrections. Okay? Corrections that come from the fact that your hydrodynamic fields are interacting, are non-linear variables. Okay, so for example, even the diffusion equation, generically diffusion constants depend on temperature or whatever the conserved density that is being diffused. And so you could imagine Taylor expanding this diffusion equation, and you'll get the leading nonlinear term will look like this, okay, which is a nonlinear correction, and you can think of it as a vertex, as a cubic vertex, right? A diffuson is allowed to split into two diffusons. And these will give corrections, so these fluctuations will give also power law corrections whose power depends on the dimension compared to the leading term. And generically, you'll have combinations of both things. You could have terms that, so a generic term in this expansion, ALM, will be an L loop mth order derivative correction to leading order hydrodynamics. Okay, so this is the structure. Hydrodynamics tells us kind of this general structure. And now the point is that each of these coefficients, apart from the first one, define a time scale, right? Power law corrections define a time scale. So each coefficient provides a possible sharp definition of the equilibration time, okay? And in fact, so a reasonable definition of sharp definition of the equilibration time is to take, let's say, the largest such coefficient, either among the first few or among all, if you want to avoid, possibilities of fine tuning. Okay, and so this is a definition that what's nice about it is that it doesn't require any knowledge about the microscopics. Okay, it doesn't depend on the thermalization mechanism, which is interesting but not universal. It only relies on the fact that hydrodynamics emerges inevitably. Okay, you're always going to have these coefficients, and moreover, it does. Let me just finish one sentence. So it does what you want to do, because why is this a reasonable definition of the equilibration time? Well, at timescales of order these coefficients, those are the timescales when these corrections become order one, compete with your leading correction. So it's a timescale at which your hydrodynamic expansion starts breaking down. Okay, sorry.
Yeah,
question.
sure. This is non-relativistic or relativistic?
This is not even, there's no boost. This is a spin chain. I can do this in any context. But let's do it for a spin chain. For a spin chain.
Just as if it is relativistic, you're kind of assuming it's in the Eckhart frame, because otherwise these ends would be vectors, right? It would be the correlation would be a tensor.
Yeah. So here this would be J0 or T00. This would be I would choose one of the densities that I have.
So okay, yes, it's Eckhart frame.
Yeah.
Okay, thanks.
Yeah. So the stress tensor is a well-defined non-perturbative operator. It has a 2-point function, and you could do that. So here I'm kind of imagining there's a single density, but indeed in a QFT you would have several components of the stress tensor. So you could do this. Okay. Any other questions? So there's no exponential decay generically, but at late times there's this power law expansion in integer and non-analytic powers of T, and this allows for sharp definition of timescales. So what do we know about these coefficients, about these A's? And this is how we're going to be able to balance this equilibration time. So we know quite a bit about these coefficients. There's, in fact, from effective field theory. So there's a long history of this effective field theory treatment of hydrodynamics. In a sense, hydrodynamics was always thought as an effective field theory since people came up with hydrodynamics. But as formulated really as an action, and where people kind of treated it as an interacting, let's say, theory of fluctuating fields, probably dates back to the 70s, both in the West and in the East, where people kind of understood some of these corrections to hydrodynamics by viewing really hydrodynamics as a real effective field theory of fluctuating fields, right? That emerges in your system. Your system, those are not the microscopic degrees of freedom, but they're weakly interacting effective degrees of freedom at late times. And since then, there's been a lot of development of these ideas in various directions, both in the kind of quantum context and also in the context of StatMech, classical StatMech, where people study kind of reformulations of these effective field theories. And in the past decade, part of this has culminated in these symmetry-based effective field theories that I'll be basing what I'm saying on. So these kind of synthesize these earlier developments and really bring it into a form where you can kind of keep track of all possible corrections systematically, the same way that you would do effective field theory in a standard model or in condensed matter systems by adding all possible irrelevant corrections. And so this systematic approach now gives you something that's actually testable. Okay, beyond just the leading order answer. The leading thing was saying things we already knew, things diffuse. But now that you have a systematic EFT, the claim is that you know any observable to, the level of precision you want at late times. Okay, by including higher and higher order terms. So this allows for precision tests of these effective field theories, similar to how one performs precision tests of various sectors of the standard model in numerics. Okay, so towards the end of the talk, I'll talk a bit about these precision tests as well. But for now, I don't want to. I'll push back this EFT stuff to a bit later. I just want to tell you one important result I think that comes out of this, which is what we know about these coefficients. So these coefficients, it turns out most of them, and this won't surprise you, are arbitrary, meaning are not are hard to constrain, are not fixed. So in particular, high derivative corrections are hard to constrain generically. Okay, a given microscopic model will have a given high derivative correction, but you can't say that this high derivative correction is always the same for all models. There is some progress, I should say, on trying to bound some of these corrections in large N theories, which I think is very interesting, but it's very difficult. Okay, so it's very difficult to constrain these coefficients. On the other hand, the corrections that come from loops are extremely easy. They're completely fixed. Okay, they are not new independent coefficients. They're completely fixed in terms of transport data that you already cared about at kind of zero loop at tree level, let's say. So to give you an example, let's look at this leading one loop correction, zero derivative one loop correction to diffusion. Here, I'm taking kind of diffusion in a spin chain as a simple example. This can be done in any hydrodynamic theory, and I'll talk about QFTs in a bit. So this correction is notice that it's also the leading correction in spatial dimensions 1 and 2. Okay, it comes before there's an extra log here, so that it comes before this high derivative correction. And it's interesting because it's this kind of leading fluctuation effect. And it turns out that its coefficient is completely fixed in terms of other transport parameters. Okay, this is what its coefficient is. Okay, that's the end. You don't need to. It's not going to be different in different microscopic models. It's always going to be this. So it only involves things you already cared about. Okay, the susceptibility, charge susceptibility. This would be specific heat if you were studying heat diffusion, the diffusion constant. And finally, the derivative of the diffusion constant with respect to the diffusing density. Okay, remember, this is where the nonlinearity came from in the diffusion equation. It's where we had this vertex from. So this is leading to a d prime squared correction to the propagator. Okay, so these are all things that you could measure, without just with regular linear response. You just measure the diffusion constant at several densities, and you can get it. So it's completely fixed. So this may not be the biggest correction, okay? And in fact, in many systems, it's not. And these higher derivative corrections are more important, but it is a correction. And so you know that it's going to bound all these corrections, right? It's going to bound the largest correction. So it tells you that hydrodynamics can't emerge. So this number in particular gives you a time scale. And at time scales of order this number, this is when loop corrections are starting to compete with tree level physics, okay? And you lose control. And so with our sharp definition of the equilibration time as the largest such time scale, this is going to bound this time scale, okay? So you'll get a bound on the equilibration time that just comes from evaluating this one loop correction. Okay, you can think of this in EFT lingo. The equilibration time is the scale of new physics. Okay, it's the scale when you start having new things. Let's talk in terms of energies. It's the scale when you start having new degrees of freedom, say quasi-normal modes or something else. But there's another scale in physics in the EFT, which is the strong coupling scale of hydrodynamics. And this is the scale you can get by just looking at loops. Okay, and the point is that the strong coupling scale has to come. Let me say different. The new physics has to come before the strong coupling scale. You can't start being strongly coupled with nothing there. Okay, so this is essentially in EFT language what this bound is saying. So this is a bound on the equilibration time that only involves these transport parameters. Okay, specific heats and diffusion constants.
Sorry.
Yeah.
Can I ask a quick question? So is this bound become trivial in a large N limit?
Yes, so we'll get exactly. So we'll get we'll get to we'll get there in a bit. The susceptibility. Okay, here it's not super easy to see, but let's see. Susceptibility is the end here. This becomes large, but this has a 1 over n. Yeah, so here you get, okay, if I write this d prime as a derivative with respect to the chemical potential instead of density, I'll get a 1 over susceptibility to the 2 over d. So it would become indeed, it would become, the right-hand side would become 0 in the large n limit, so the bound would become trivial.
Yeah, I was just thinking from the perspective of loops.
Exactly. Loops are suppressed. Exactly. Yeah. Loops are suppressed. So indeed, and loops are an example. So large n is a situation where, you know, the cutoff of hydro comes entirely from higher derivative terms, right? So yeah, so there you have to work with this. Yeah, so this is kind of, I think it's interesting because it's orthogonal to, you know, large n approaches. So we have many large n approaches to transport, which are very powerful. This is instead kind of more general, but it's particularly interesting at small n, where these loop effects are word-away. This is a bound that applies to both classical and quantum systems. It's not the Planckian bound yet. Okay, it doesn't have an hbar. And in fact, when we go to the numerics, I'll show you some classical systems that's thermalized with this time scale. But it still has quantum implications if you add a few ingredients. If you know, in particular, if you know something about the density dependence of your diffusion constant or the temperature dependence of your diffusion constant. And this is what we'll see now. Actually, let me not do this example. Yeah, let me do CFT. So let's think about diffusion and hydrodynamics in a CFT. So this is a situation where we know a lot about you know, the equation of state and diffusion constants because of scale invariance, right? So that basically the equation of state is so here I'm just going to consider a CFT without any extra symmetry, no U1 symmetry. The equation of state is almost trivial, right? It's just fixed up to a dimensionless number, so I can parameterize it by the entropy density, for example. And it's fixed by scale invariance to the temperature to some power. And similarly, the diffusion constants or constants or you know, shear viscosity is fixed to the temperature to some power times the dimensionless number. Okay, and these numbers, you know, are so the entropy density. This is something that just depends on the equation of states. Okay, this is a equilibrium property. It's much easier to access. Say with numerics, you can do imaginary time numerics to access this quantity. And so this is a fairly easy thing to get even in an interacting system. Whereas this D naught is really a transport thing. Okay, this is much harder to get in a generic system. Very good. So good. So basically, all we have to do is plug these things in here. This chi is the specific heat, which will be a derivative of S with respect to T. And what you land on is something that's almost a Planckian bound. So okay, it's not too surprising, right? You have a CFT. The right hand side will have to be dimensionless. But the point is that there is a bound. Okay, there is a bound, but the right hand side is not quite 1. Okay. And here I'm not keeping track of order 1 factors, but you can do it. So you know there's some order 1 factor here, but up to these order 1 factors, the right hand side involves the equation of state, which, you know, we're not too worried about. This is easy to evaluate in QCD or in any interacting system. But it also still involves this transport parameter, which is a complicated beast. Okay, so we're not quite there yet. However, this is still already an interesting bound. In particular, we could put the diffusion constant back on the left and view it as a lower bound on the diffusivity or the shear viscosity. Okay, and this is something that, you know, people have been searching for a long time. Lower bounds on diffusion constants or viscosities have been long sought after. They've been conjectured for some time. This is a proof of a lower bound on shear viscosity of a CFT. Which involves, you know, the right-hand side is maybe not what you wanted, but it is what you get, and it involves some factors, and in particular, it involves this equilibration time. Okay, you know, if you imagine a system that's strongly interacting, you might expect this to be 1, so the bound would be 1-ish, but in general, this is what the bound is. Okay, so it's a lower bound on the shear viscosity. Good, and I think someone should correct me if I'm wrong, but I think lower bounds hadn't been proven before, but please correct me
I'm sorry, but once again,
Yeah.
if I take large N limit, then this
Yes.
simply will be eta over S larger or equals than 0.
Correct. It becomes
So there
trivial
is no
for large N
bound. So
systems.
that does not provide bound in holographic models. And in
Correct.
fact, in holographic models, it was shown. So I'm talking about systems where there is large N. Then
Yes.
again, there is no bound. It can be eta over S larger or equals than 0. So that's the status. Even in
I see.
holographic.
Okay. Actually, I'd be interested in. So this is without breaking any symmetries.
Yeah, it's in models with high derivative terms, so you can
Interesting.
pretty
But
much.
you're saying you don't have problems of causality in the bulk. It's still
You
consistent.
don't, because it's special, so-called topological gravities.
Interesting.
Where,
Okay, I actually would want to ask you a bit about this, but it's interesting.
Okay.
So I think you're saying that I couldn't have done better, which makes me feel good because you're saying it better be 0 in holographic, at least in large N. Okay, interesting. Yeah, thank you. Thanks a lot for the
Can I just make
Yes.
one comment? Yeah, that now we have heavy ion collisions with hadronic collisions in small systems, and there is also ultra cold atoms. The experimentalists are learning to make systems of ultra cold atoms with very few degrees of freedom, literally putting in one atom at a time to see the smallest fluid.
Yeah.
And this bound does not seem to be experimentally supported, at least if you interpret the observables that they measure as hydrodynamics. It seems, and this is very intriguing, that the effective eta over S, or the equilibration time or whatever, is completely independent of the degrees of freedom. Just as a comment.
Completely independent of what? Of the number of degrees of freedom? Or...
Yeah, we have the experimental. We have some.
Sorry. The number. This is a local number of the degrees of freedom. It's not the number of atoms. It's the number of atom density.
Yeah, I know.
It depends on the trap, but it's probably roughly.
But you make the trap with the same volume, and you just put in one atom at a time.
Yes.
And basically, as soon as statistics turns on, you seems to see. With cold atoms, this is much more preliminary than with small systems in hadrons, but nevertheless. It seems that this equation doesn't hold experimentally.
So I think you're saying it's not saturated. So indeed, the bounds don't need to be saturated, but they do need to be satisfied. And this one, this equation isn't. There's a proof. So
no, but you vary.
But it could be that the assumption. So it depends on what system you're applying it to. Here, this is for a CFT, which won't quite apply to.
You can vary the right-hand. What happens is that you can vary the right-hand side, and you can check if the left-hand side varies.
If the bound is saturated, right? That's a check of whether the bound is being saturated.
Okay, that's true.
Yeah. The bound, I should say, is highly non-saturated. For example, at large N, right? Let's say large N, not the examples that Alex was mentioning, but the kind of vanilla holography, right? This thing is order 1 and this thing goes to 0. So, this is not a bound that's always going to be saturated. I think it's particularly interesting at small n, where by n, I really mean the local degrees of freedom. Okay, still many particles, but the density is order 1. Okay, the number of fields is order 1. And there, okay, so this at least for CFTs, you can just prove this. Good. So okay, but this is not exactly what I was targeting, right? I was trying to get a bound on this equilibration time. So here I still have this right-hand side that's a little bit complicated, and my bound involves both the viscosity and equilibration time, two quantities that are not obvious to determine from microscopics. You can measure both of them, of course, but they're hard to. They're still a bit complicated. To get a bound on the equilibration time alone, what one can do is combine this bound with another bound, a causality bound on diffusion. Okay, so this is a bound that was suggested in this paper, which is simply the statement that diffusion naively is acausal at early times, goes outside of the light cone. Of course, that's not a problem. Hydrodynamics only emerges at late times, but it tells you that hydrodynamics can't emerge too soon. For a given diffusion constant, it gives you a bound, at least parametric, on how early hydrodynamics can emerge. Okay. Otherwise, it would lead to finite spectral densities outside of the light cone. Okay, so this is what this bound looks like. And there's a squiggle because this is not my sharp definition of the equilibration time, right? And in fact, I wouldn't know how to get rid of the squiggle here. So that I think that's an interesting question. But for now, okay, let's be happy with a parametric bound. So this gives you another bound. They phrased it as a bound on the upper bound on diffusion constant, but you could view it as another bound on the equilibration time. So what's interesting now is that we have two bounds on the equilibration time, one that involves d and one that involves 1 over d. So if tau is supposed to be both bigger than d and 1 over d, it has to be bigger than 1. Okay, and if you keep track of the powers of equation of state of S naught, this is the final bound you get. Okay, so one essentially obtains the Planckian bound for non-large n systems by combining this fluctuation bound with a causality bound. Okay, so in CFTs are causal. They will have to satisfy this bound. So so here I think there is a little bit of room for improvement. It would be nice to make some of these inequalities sharp. So the the fluctuation bound is sharp. This equilibration time is sharply defined, but it's not exactly clear how to combine it with causality. So that would be interesting to do. I should say that at large n there have been some sharp causality bounds that were made. That were made possible, but really thanks to large n, and it would be interesting to kind of see if there's something that can be done in between to obtain a sharp bound to sharpen this bound, let's say, on the equilibration time. Okay, but now the thing we have on the right-hand side is really just 1, except for this factor of, let's say, n squared to the 1 over d. Okay, so indeed, for the Ising model, this says that the Ising model cannot thermalize faster than 1 over t. For QCD, it also means that. Okay. S naught for QCD is something like 10-ish, and you take the third root, it's going to be 1. So for QCD, this is the Planckian bound for QCD. Okay, maybe not for holographic theories, but for QCD and the Ising model or day-to-day theories, it's the Planckian bound. Okay, let's see. So sorry. Okay, good. So in the last part, maybe I'll pause the last part before going on to the last part, where I will slightly switch gears and talk about numerics. Are there any questions before that? Oh, I'm not monitoring the chat, but yeah.
Yeah, let me just draw the attention to the references that Alex Buchel has posted regarding the high derivative corrections and the corrections to eta over S chemical, including chemical potential, just so people are aware of it. I don't want to distract from your talk, but just before it disappears.
Yes, no, that's a good point. I'm going to just copy it somewhere so that I'll still have access to it after this falls into a black hole. Okay, any other questions?
Sorry, can I maybe make a comment? So there has been, at least on a holography part, there has been a study of systems which do not equilibrate. So those are not integrable systems. And so this research goes, under the name of weakly turbulent instability in ADS. And so at least in the holography, there appear to be examples where you have a strongly interacting system. So we're talking about holographic models in asymptotically ADS that fail to thermalize. And also on a kind of field theory part, we know systems like Fermi-Pascal type of models, where there is also no thermalization.
Yes.
So I'm just saying that on one hand, you are thinking that, okay, there is this universal perspective. Yeah, so I guess, right. So, and then all of these things that you're just mentioning, many body localization and all of that. So I would say that just a starting point that everything would thermalize is a bit
too strong. Absolutely. Yeah, no, I'm completely on board. Indeed, there are very interesting exceptions to this kind of axiom that I started with, right? That are subject of, and I think that's very interesting. Indeed, so the proof I gave assumes the system thermalizes. So I'm only, in fact, even the definition, right? You probably wouldn't even want to define an equilibration time. So yeah, the definition I gave assumes the system thermalizes, where by thermalize I mean hydrodynamics emerges. And there are some counterexamples to it. They're the ones you mentioned, integrable spin chains, integrable QFTs. There's also systems that are not microscopically integrable, but involve disorder, which are not very well understood. In fact, yeah, so maybe I'll leave it at that. And so it would be very interesting to understand what is the landscape of many body quantum dynamics at finite temperature. There's thermalization as one option. Within thermalization, there's several kind of subcategories. Things can diffuse. Things can also have different power laws. There's KPZ physics in low dimension. But you could also have exceptions to thermalization. You could have violent departures from thermalization, like integrability, MBL, glassiness. You can also have more subtle departures from thermalization that people have been studying. And so I think those are very interesting questions. And in fact, it's a perfect segue into this numerics part. So I think this is where a lot of these effective field theory methods can help, because this numerics, especially in quantum many-body systems, is extremely costly. It's hard to have good quality, long distance, late time, numerics kind of in the thermodynamic limit, obviously. So it's easy to claim victory too soon, right? So to think you're seeing some asymptotic behavior and actually getting the wrong one. So even in systems that thermalize, people often try to extract this power law decay of correlation functions, and the power will tell you what kind of dissipative universality class your system is in. Okay, diffusive being this 1 over square root of t. And when you have access, typically in quantum many-body systems, you don't have access. You don't have the luxury of large hierarchies, and it's very difficult to do these things, to extract reliable universal data out of limited numerics. And this is where the effective field theory can help, because it ties in a lot of observables. Okay, effective field theory has a few unknown Wilsonian coefficients, but they enter in everything. So you have a hugely overdetermined problem where any correlation functions, corrections to correlation functions, nonlinear response are all controlled by the same quantities. So you can, if you have your numerics, that's poor man's numerics that doesn't go to very late times, you can just look at many observables and get much more reliable fits to these things. So a central motivation of what I'm doing is to kind of help numerics do this, to identify possible deviations from thermalization, deviations from this fine structure of thermalization. Okay, so yeah, so the motivation for the numerics is twofold. One is this, and the other is just to test some of these effective field theory claims that I've been making. Good. So the effective field theory we'll be testing is the following. Maybe in the interest of time, I won't go too closely, over it. Probably some of you have heard of these. The idea is to just, you're interested in thermal correlation functions, which will be generated by this generating functional. And effective field theory is a representation for this generating functional in terms of weakly fluctuating fields that are related to densities. Okay, the assumption of hydrodynamics is that density is the only light degree of freedom in EFT sense. It's the only long-lived degree of freedom. And because you're evolving a density matrix, the right thing to do is to evolve it on a closed time path, Schwinger-Keldysh contour. And because of this, you have a kind of doubling of degrees of freedom where your density has a friend related to what some people call the noise field in hydrodynamics. Okay, so that's what these effective field theories look like. So without going into the details, let me just show you what the kind of leading, simplest effective field theory looks like. So this would be the effective field theory of a single conserved quantity. And you just, there's this initial very important leap of faith, this assumption of thermalization, which says that the only right degrees of freedom at late times are densities. Other than that, everything is very straightforward. You just use symmetries to constrain your action, as usual in effective field theories. And so this is what it looks like. So you have two fields, the density and the noise field, and you write it in a gradient expansion. Okay, so so there's going to be high-derivative terms. I didn't write them all. You have a diffusion equation that you see here, and the CFT comes with Wilsonian coefficients. Okay, the effective field theory will never tell you what conductivity is, what diffusion constant is, but it will parameterize your ignorance in a few Wilsonian coefficients. Here, these coefficients can also depend on the density, on the field itself. okay? And this will lead to nonlinearities in the effective field theory, okay, by Taylor expanding these quantities. So we see something interesting. We see that nonlinear response, coming from these nonlinear, non-Gaussian terms in the effective field theory, is in a sense tied to linear response, right? If your diffusion constant has a certain dependence on density, which you can completely measure with linear response, right? You just do your transport measurements at various values of the density. This will inevitably lead to nonlinear response. It will be tied to nonlinear response. Okay, this is something that's the first kind of, in a sense, obvious consequence. Very good. So I'll talk about some applications or some numerics. I'll probably focus on these two probes. So the first that we'll talk about is precisely these power law corrections that were central to obtaining the bounds. So we're going to test very precisely these power law corrections to hydrodynamics in various numerical models, classical systems and quantum systems. And then we'll look at nonlinear response and how nonlinear response is also completely constrained by effective field theory. So let's start with these corrections. And again, so motivation for this is work done by these people. And the central motivation for this is to help numerics, okay, beyond just testing effective field theory. So let's say you're trying to identify the power law, diffusive power law, and you only have access to intermediate times. If you had access to very late times, you would see, that you're making a mistake. But because you only have access to early times, it's very difficult to reliably extract transport data. And the effective field theory can help because it tells you what these corrections are. So let's try to measure these corrections. So I had this slide before of the corrections to the 2-point function. We can even make a much stronger prediction. We can look at the 2-point function resolved in space, like this. So this is the density 2-point function, J0, J0, as a function of space and time. And what you find, so you again have these power law corrections and these loop corrections. And the coefficients that I had before, so these coefficients A00 and so on, become scaling functions of this scaling variable, the natural scaling variable in the context of diffusion, x over square root of t. Okay. And these, what's crazy is that these scaling functions are universal. They're completely universal. They're universal functions of y. For any diffusive system, they'll be the same. So some of these corrections, they come with non-universal coefficients, right? Higher Wilsonian coefficients. But these non-universal coefficients multiply a completely universal function. So you measure it at one value of y, you know it at all the other values of y. Okay, it's highly overdetermined. So here we really see the predictive power of the effective field theory, right? It's predicting whole functions worth of information. This very first function, you know it. This is just regular diffusion. So it's a Gaussian in space and time. That's how diffusion spreads. Here I'm doing 1 plus 1z, but you could do this in any dimension. So this is what it looks like. And by the way, so the overall scaling of this term, you can kind of get it with a simple scaling argument. But the form of this scaling function, even for simple diffusion, to get it, you need to actually solve the diffusion equation. So you need to know the details of the action or the equation of motion. And similarly for these higher order corrections, it's easy to guess what power they come with, right? We kind of guessed before using hydrodynamic corrections, but these universal scaling functions, you really need the effective field theory to get them. And so you can do that. So let me show you the universal scaling function corresponding to the one loop correction. Okay, this is what it is. It's plotted here. So it's going to be the same for every diffusive system. Okay, heat diffusion, spin diffusion, and you could do the same for for sound modes and so on. So it's an entirely universal function. The prefactor is not universal, but it's the one that we discussed before that involves d prime and the diffusion constant and susceptibilities. Okay, but otherwise it's an entirely universal scaling function of this scaling variable. And you can go on. And so this is really, this is going to be very falsifiable, right? There's a lot. It's a strong statement. I'm saying that the entire correction comes with this one. Okay, and this is the one loop diagram that produces it. Okay, so let's test this in numerics. So, so the first kind of simplest numerics that we looked at is just a classical gas of of particles. So imagine you have a string of ones and zeros. Your ones are particles that can either hop left and right, and they do so kind of stochastically. So there's a probability to hopping, and the probability depends on whether you have neighboring particles. So in this sense, it's an interacting classical model. They want to repel or attract in some way. So this system thermalizes. It's classical but not integrable. And it turns out, so the reason we chose it is that it's simple enough that actually the diffusion constant as a function of density of particles is known analytically. There's just you can solve it, which is kind of nice to test the effective field theory because there will be zero fitting parameter. Okay, everything entering in this expression, the leading part, the subleading part, will all be completely fixed. So here I plotted the 2-point function in this model. So here you can see it, converge to a 1 over square root of t at late times. And you see there's some deviation at early times. So here I'm plotting the spatially resolved 2-point function of the density, J0, x and t, in terms of the scaling variable. Okay, y is x over square root of t. So you see this Gaussian. Here I plotted it in such a way that it should collapse to the same function, right? I multiply by square root of t, so that you just get this function, and you see indeed that the curves, the different colors are different times. Yellow is latest times. You see that they almost collapse to this theory prediction. So red is just the theory prediction with a known diffusion constant. So they almost collapse, but they don't quite collapse. There's a small deviation, right? Which we expect because we expect to have higher derivative or higher, power law corrections, fluctuation corrections in this case. So what we can do is now subtract this numerical data from the expected analytical answer. So I remove analytically, this term, and measure the difference. Okay, and so here this is the difference that I'm plotting. And the black dashed line is the theory prediction with no fitting parameters. Okay, this is just this term. We know all the parameters in this expression, and the different colors are the numerics. So you see this exceptional agreement, like the percent level agreement of the whole function with zero fitting parameters. So to me, this is really kind of very satisfying confirmation of these effective field theory treatments of hydrodynamics, and they really allow for these precision tests. Right, this is a very small effect, and yet you have this whole function's worth of data. We even looked at situations at models where the leading correction was 2-loop. So for example, if you have a system that has particle hole symmetry, you will have a cubic vertex, and your first loop correction will be 2-loop. You can again, compute this with effective field theory. So here the effect is very small. We weren't, qualitatively it works quite well, but it was a bit harder to get as good of a quantitative agreement just because the effect was quite small in the system we looked at. And I should say this is also quantum. So we also tested this in quantum systems, including in Fouquet models. Going into this, it wasn't clear to me that these effective field theories would apply even to these kind of non-Hamiltonian systems, unitary circuits with diffusing spin or charge, but it really seems to apply perfectly well to these systems. Good. And in the final 2 minutes, let me talk a little bit about nonlinear response. So you can, the same, and this is work done by my student, Richira. So the same effective field theory controls many other observables. Okay, that's really the predictive power of this, of effective field theory in general. And in particular, it's going to control nonlinear response, higher point functions. Okay, and what's kind of neat is that it's really the same vertices. Okay, diagrammatically, once you have these diagrams, it's kind of obvious, but it is the same vertices, these same numbers that are controlling nonlinear response. So when you're doing your numerics, if you're trying to get a very precise measurement of these numbers, you have all these observables that are kind of redundant in a sense. They're independent numerical observables, but from the EFT perspective, they come with the same parameters. And so you can do these tests, 3-point function. So here we looked at the 3-point function, for example. 3-point functions, higher point functions have a lot of information, right? There's a lot of coordinates, 2 coordinates, 2 times. Here, just to simplify this slide, I set a lot of things to 0, but you have the whole functional form of the endpoint functions with many coordinates, and you can really do these kind of tests, quantitative tests against numerics. This is some other tests we did in quantum simulations. Okay, but yeah, so I think I probably will not talk about this. You can also look at correlation functions of other operators. I will just say one last thing, but that's very, very fast. I just wanted to mention, so I put a few things under the rug in discussing the universal, the bound, the Planckian bound on CFTs, because I was kind of using, I first talked about diffusion and spin chains, and then said, okay, well, you can do the same for CFTs. Of course, CFTs have much richer hydrodynamics, and with sound modes and diffusion modes. And loop corrections are actually a bit subtle. So one thing I realized is that even the scaling of the corrections, let me see if I have, I see, yeah. So the scaling of the corrections, of power law corrections to hydrodynamics, say along a sound front, is not what you would expect from classic long time tail type papers that people are quite familiar with. And the point is that, so specifically, well, okay, I'll just say qualitatively, but even the power of, let's say we're along this sound front, you have this leading behavior that goes like 1 over T naught to some spatial dimension, to D over 2. The leading correction is not what you might have expected from what we know the leading correction to viscosity, the fluctuation long time tail correction to viscosity is. The power is different. In fact, they're a bit more suppressed because of kinematics of sound modes. This is kind of interesting because it actually says, shear viscosities, you might have heard the statement that in 2 plus 1D they run, they're log renormalized. And so in the IR, they just are fixed by thermodynamic properties. And so there's kind of no shear, you might think there's just no shear viscosity of a 2 plus 1 DCFT. But actually it says there is a shear, it is a well-defined quantity, the shear viscosity of a 2 plus 1 DCFT. You can just look in real time and space, and you'll measure a kind of actual shear viscosity. The corrections will not be logs, that will be power law suppressed. Okay, I just wanted to mention this because I think it might, it could interest some people. But so all this was taken into account into actually establishing the bound in the case of CFTs. Okay, so I'll stop there. Thanks a lot for your attention and questions.
Thank you very much, Luca, for this very interesting talk. I'll let others ask questions first.
If I may, yeah, I have a question. In this last section where you mentioned nonlinear response, and especially the connection with the EFTs,
yes,
it seems you often just consider order correlators, and
yes,
I imagine you have the EFT defined, as you mentioned, in the Schwinger-Keldysh contour.
yes.
But could you gain more information if you consider a non-order correlator that would need to be defined in higher order
yes,
time folds? And in particular,
yes.
maybe one can make a connection with the chaos bound.
Yes, absolutely. Yeah, no, that's a very good point. So here, for 3-point functions, they're kind of all fixed by a Schwinger-Keldysh contour, a single Schwinger. But indeed, as soon as you have 4-point functions, you can have orderings that cannot be reproduced by a single contour. So then, indeed, the EFT, you'd have to generalize it and put it on a 2-legged contour. And indeed, you might imagine that there's room for new transport parameters that are kind of, in some sense, chaos, transport parameters. I don't know. Yeah. I don't know if you would see Lyapunov. I'm not completely sure, actually. I think it's something very interesting to do. But yeah, there's room for more. Indeed, what we did here was only time ordered and some non-time ordered, but that are reducible in some sense to time ordered correlators of densities.
Thank you.
Sorry, I didn't hear the Julius question or comment, but possibly following up on that, the Maldacena, Schenker, and Stanford bound on chaos and on the Lyapunov exponent in many body systems. How is that related to the thermalization time that you would that you were discussing here? Do you see a relation?
A relation, yeah. So qualitatively, yes. Like in the sense, they're both time scales are very long in weakly coupled system. You can get them perturbatively. They're going to go like 1 over coupling squared, where your coupling is the 4, let's say 2 to 2 scattering. in that sense, they're kind, and so, but quantitatively, like, you might ask, oh, is one equal to the other, up to some 2 pi or something. Yeah, this I think probably not, although, yeah, I mean, the Lyapunov exponent is not really a sharply defined thing away from large n, so maybe you don't expect a universal relation between the two, but maybe in large n systems there is a universal relation between the two. I'm not sure. Yeah, that's a good question.
Yeah, just using that as to point out 2 relations that I could see. So one is the idea that black holes and their Hawking radiation can be viewed as many-body quantum systems. That is what recently has been called the central dogma of I guess the information question, or Hawking radiation, entropy of Hawking radiation. And so if you view a black hole and its Hawking radiation as a many-body quantum system, in principle you could apply an effective field theory description to it, like you do to spin chains or other many-body quantum systems that you have in mind, that you have discussed today. And then a possible question arising from that is what does such an EFT tell us about black hole physics, and possibly about quantum gravity in that context?
Yeah, I think it would be, I mean, related back to the just previous question, you could imagine extending these kind of hydrodynamic effective field theories to also capture these other probes. So just put a hydro EFT on a 2-legged contour, for example, and see, that would be one thing that could unify chaos and hydro, if it's, yeah. But in that case, I would expect more to see it as kind of 2 independent Wilsonian coefficients of an effective field theory. But and yeah, sometimes there are non-trivial relations between these coefficients, and that would be great if one could show something like that.
Thank you. Giorgio had raised his hand.
Yeah, thanks. Can you go to the slide of the universal corrections to diffusion, where you had all the
numerics, or this one?
Yeah, this one here. I mean, my worry is, I sort of mentioned it in the talk. The point is, are these coefficient physical quantities? In principle, if you know time, it's easy. You sort of measure the correlator in time, and then you isolate, different powers in time. So obviously they're observables. Except that you are talking about local equilibrium, and certainly if you have Lorentz invariance, but I think also in a relativistic limit, you kind of have to know what the clock of the volume cell is. And in the Schwinger-Keldysh effective theory that you were talking about, as you say, I mean, you have a density as a starting point. The density, your degree of freedom, not the current, the density. But if your degree of freedom is the current, so I mean, the left-hand side is a rank 2 tensor, the right-hand side has to have Lorentz covariant things as well. You might confuse if you have any kind of fluctuation of your reference frame, so basically fluctuation in flow, fluctuation in momentum, all of these power coefficients will be mixed together and will not be measurable in theory, like if you dunk an experiment, unless you have an infinite number of particles. But then, but then you have no fluctuations.
Yeah, I think I understand the question. Or do you want to? Okay, yeah.
Yeah, just as a sort of, I mean, in relativistic hydrodynamics, you have the Landau frame, the Eckert frame.
So okay, no, I understand. Yeah, so there's two separate things. One is the well-definedness of these things in general without EFT, and the second is how to get predictions for them in EFT. So let me first address the first question. So of the well-definedness of this thing. So the quantity I'm looking at on the left is a 2-point function of the stress tensor in a thermal state. Okay, this is defined in any context, in QFT. It's a well-defined quantity. If you want to relate it to experiments, you'll have to figure out linear response and so on. But just it's a well-defined thing even if hydrodynamics doesn't exist.
Mhm.
Okay, and it has these power law expansions. Now the EFT prediction. So then the next question is how are you sure you have the right EFT prediction for these things? And I think indeed these EFTs are tricky. It's not completely obvious. Their field redefinitions change the frame, which shouldn't affect things. The operator team is a well-defined microscopic thing, but your fields, you could choose whatever fields you want. They're in a path integral, and indeed, so I think I think by now we have some confidence on what is the right thing to do, but that's also why I'm doing this numerics, right? To make sure that we're doing the right thing, that these effective field theories are doing what we are giving the right answer.
I see we have probably one more question and time for one more question. It looks like Navid has one.
Yes.
Or a comment.
Hi, Matthias. Hi, Luca. Thanks a lot for the nice talk.
Thank you.
I have okay, it was great. I have a question maybe in the next slide when you compare your results with numerical results with this. Maybe, oh yeah, exactly here. I would like to understand how to compare the first loop results with the second loop results. Here, it seems that you can confirm the numerics just by using the first order loop computations. Is there any physical reason why the second loop corrections are not important here, although we know that this theory is not kind of large n theory?
Yes. Yeah. So the hydrodynamics is a controlled expansion even away from large n, thanks to the fact that interactions are irrelevant. So 2-loop has a higher power of 1/t.
Okay.
Yeah, so then you just need to go to late enough time. So then it's a question of, is your numerics good enough to approach this very late time regime? But as long as you're able to access very late times, you're guaranteed that 1 loop will be bigger than 2-loop and so on. So it's controlled.
Okay, great. But I was wondering if in the time interval that you were showing at that plot, t and maybe exactly here, are these t and square root of t's? Oh, okay, 10, 1. Okay, great.
Yeah. So here, right here you see the bare data. Red is the pure tree level answer. So you see there's a deviation. At late times you almost nothing. You see a deviation, and what we're using is the fact that the leading order, the deviation is just due to 1 loops, because there's probably a remaining deviation here. We can see it doesn't perfectly agree. We tried fitting it to 2-loop, but at 2-loop order there's also high-derivative terms. So there it's a bit there's a little more moving parts. It's a bit harder.
Sorry, I confused this, but with y. Sorry, that is t is large, so 1/t is much smaller than 1 square root of. Okay,
exactly.
Great, thanks.
Exactly. Yeah, t is large. Yeah.
Okay, we usually have a minute of informal discussion after the recording stops. But for now, I would like to thank Luca for an inspiring talk and presenting very interesting results. Thank you everyone who contributed during the talk with questions and comments. And I hope to see you all next week. We have Karl Landsteiner next week, and we'll be sending out an email. So thank you again, everyone, and see you next time.
Thank you.